transfer, and this being the third one. So radiation is primarily an electromagnetic wave phenomenon. Right? Unlike conduction and convection, you don't require a medium, right, for transferring heat from one point to another point by radiation. Radiation can transmit even in vacuums. That doesn't mean it won't propagate in the presence of medium. Right? So radiation can propagate either in the presence of medium or in the absence of medium. Whereas conduction and convection are possible only in the presence of medium. Right? You see, so far, if you recollect what happened in conduction, there is a material medium and heat is transferred from one point of the medium or body to another point. That means this body itself is the medium. Similarly, there is convection. So convection, there is a fluid adjoining the solid surface. So therefore, medium is required for conduction and convection heat transfer. But for radiation, that's not a necessary requirement. It's absolutely okay even if there is no medium. So now, see, you can this radiation, in fact, is much more than just thermal radiation that we are talking about. Though our discussion is confined to thermal radiation, so there are many other radiation waves like X-rays, gamma rays, ultraviolet rays, infrared rays, microwaves, radio waves. So just you can imagine this. For example, if you take radio waves, right? So somewhere there is a source. Somewhere voice is generated. Somebody is speaking. But looking at, sitting at a different place, we are able to listen to it. Right? How is it happening? So at a certain frequency, that those waves are propagated through the atmosphere that is there, and then if you tune in your receiver at the same wavelength and frequency, then that will catch it. The same way the radiation heat transfer also takes place. It's no different, but the wavelengths are different. These radio waves are towards the larger wavelengths, and the gamma rays, X-rays, these are towards the smaller wavelengths, right? Whereas this thermal radiation is somewhere in between, in the order of wavelength of around 1 micrometer to probably around 100 micrometer. That's how it happens, right? So this thermal radiation also similar to that. You can imagine, for example, sun. If you take sun is the source of heat and earth is the receiver. So it is passing through many different layers, right? It's not one single medium. So one perfect example is the heat transfer from sun to earth. So just like imagine the radio waves transmitting from source to the receiver, the same radiation, thermal radiation which you are calling it as, transmitting from sun to the earth, right? In a different wavelength range and temperature range. Okay. So now we know very well that any body which is above absolute zero temperature. See, what is the lowest possible temperature? Lowest possible temperature is 0 Kelvin, right? Don't switch on the fan. If they are not comfortable, they will come here. So any body which is having more than 0 Kelvin, so that will emit certain energy in the form of radiation, which we call radiation emission or simply the emission. And such energy, right, which is transmitted by radiation is proportional to the temperature of the source, right? So if you see here, there is a body which is at certain temperature, Ts, which is obviously greater than 0 Kelvin. So it emits energy, right, in all the directions, and then it can hit the body whichever is coming in that way. So here this is a body in a large enclosure. So now, apart from the example that we have taken sun to earth, you can also think of an electric bulb, right? So in the electric bulb there will be a filament inside, and the heat what's the medium between the filament and the bulb surface, or within the bulb, electric bulb? Now what medium is there? Is there anything that is present? Any medium? No medium, right? It's perfect vacuum. So now how that heat is transmitted from the filament to the surface of the bulb? It's by radiation, right? See, the intensity of radiation will be more at higher temperatures. Please understand now, as we go further we will see. Stephen Boltzmann law says the magnitude of heat transfer by radiation is proportional to 4th power of absolute temperature. So normally in conduction and convection it's just the temperature difference between the two bodies. But now if you consider two bodies, it is temperature to the power of 4 of the first body minus temperature to the power of 4 of the second body. So that's huge in quantity compared to what you get in conduction and convection. So the radiations are predominantly present where there are higher temperature zones. See, this thermal radiation, one way of understanding it is electromagnetic wave phenomena. The other way is considering it as propagation of particles like photons and neutrons. See, you can visually see them in certain situations. For example, those of you living in villages, right, where those old houses have ventilators on the top of the building, right, to the roof, because there are common shared walls. You don't have provision to have windows in the walls, and this is volumetric phenomena and this is surface phenomena. Suppose gases and also fully transparent or semi-transparent solid bodies. So they emit radiation in all directions, right? It's 360 degrees. So it's a volumetric phenomenon. Suppose there is a body emitting radiation. It doesn't emit just in one direction. It emits in all the directions. Opaque means it doesn't allow any rays to pass through it. So underside of it there will be no propagation of radiation waves. So they will only propagate the upper side. Now it will cover just like hemisphere, half of the sphere. So this is called surface phenomena. Now mathematically, right, these thermal radiation particles or waves transmits at a speed of the light, right, equivalent to the speed of the light. And the speed of the light is linked to what? Frequency and wavelength. So the product of wavelength and frequency will give you the speed. So that's how the radiation is governed by, right, connecting the wavelength and frequencies. Okay. You may note this down, right? Before that. Is said to be transported by particles like photons and neutrons. Also, it can be propagated in the form of electromagnetic waves. Electromagnetic waves on the surface. Heat transfer from sun characterized by wavelength in brackets lambda and frequency in brackets mu, which are related through electromagnetic radiation spectrum, can be seen. So this is wide range of wavelength. You see, this starts from extremely low wavelengths, gamma rays, X-rays, and then extremely large microwaves. Even radio waves also falls here. In fact, they fall beyond this, beyond 10 power 5 micrometers. So these radio waves and microwaves are significant for electrical and electronics engineers, right? There is a microwaves labs you can see if you want, right? So their subject deals with this part, larger wavelength, wave phenomena. Whereas this is significant for physicists and also nuclear engineers. Right? That's where they work with. We also know X-rays we use to see what's happening inside the bodies at cellular level. We use X-rays, so those rays can be sent and then reflected back, and then they will get the image of the bones, right? Or the physical condition they can go and see. It's like putting a torchlight inside and then see. So that is one thing. And here, this is a particular range from about 0.1 micrometer to 100 micrometer. Thermal radiation ranges, which consists of infrared rays, fully, part of ultraviolet rays, and within that this is the visible range, very narrow visible range. You can see the rays are entering only in this range from 0.4 to 0.7 micrometers. So beyond that, on either side, you cannot see with your naked eye, right? So next slide, radiation properties.